Okay. Um, I've long been concerned about the fact that when it comes to where we are uh, with the material, that um, based on like the problems that you're working on or asking questions about, that you guys are like either towards the end of chapter 2 or very beginning of chapter 6. Um, Whereas in terms of what I'm covering, I'm like, getting into chapter 8. Um, so, so in other words, basically like a full chapter ahead. Um, so I've decided to do something about it, and that means, um, and the thing is, I realized that my flexibility, shall we say, with due dates has is a contributing factor here because that has been taken advantage of to a far greater degree than I've had happen before in other classes, regardless of the level. But in any case, I've what I'm doing right now to try to restore the rhythm, if you will, to the class that I had in mind from the beginning, and I made clear at the beginning, and the class as a whole has not gone along with, much to my consternation. I've done as much as possible hitting the reset button today, right now, and um, so I'm going to show you what that means in terms of schedule, because I've looked ahead because we have a second course that some of you will take, or maybe only a few of you, but there's room in there for anything that I don't get to cover this semester. So a couple things have been deleted. Okay, so here we are today, October 12th. I've deleted the following things. I've deleted the midterm exam. I've also deleted Chapter 9. Well, Chapter 9 is not fully deleted. It's simply moved to the second semester. It doesn't, and 460 is not a prerequisite for anything other than 461. So it doesn't create a problem anywhere else in the curriculum, and there's enough time to cover everything, um, in the spring. That means deleting one homework assignment. That would have been homework 5. Um, so since it's obviously physically impossible to have you guys immediately catch up to where I am in the material, think of this as I'm coming backwards to get you and drag you along kicking and screaming if need be. Um, so these are for due dates. Now, I would not fault you at all if, when I say that I'm going to enforce these with the late penalty stated on the syllabus page, 5% per day, that you'll be like, yeah, right. So I could understand you saying that. But the only reason I didn't already is because there literally was a hurricane. Um, so since so so what we're going to do is these are the topics of the day. So about 7 of you answered my email yesterday about which problems pose the most difficulty. I was hoping the union of those problems would be smaller than it actually is, but it amounts to about half the explorations in section 2.2, like 2 or 3 problems or so in section 2.1. Um, so so to make things so in exchange for making these things, giving you guys a chance to get caught up and have us all literally in the same page, um, I'm going to remind you of what I said at the beginning of the semester I expected to do. And what I probably should have done the first time, put it in writing. Um, That's strange. I don't know if you can see this, so I'm going to make this window bigger. Here I have large in caps, and then up here I have huge in caps. That's supposed to be bigger, but it's not. Ah, okay, silly me. Okay, now, what I need you guys to do, this is not a long list, but I'll number it anyway. Okay. Check the schedule. See what I'm going to cover on that day, unless there's a natural disaster. That is going to be the section of a day. You'll be able to ask. I mean, you obviously I'm still going to have time each class period for questions, and those questions can be on whatever section it is. I'm not going to restrict on that. One of the reasons why I got tossed to midterm was it opens up 2 class periods. That makes it easier to do everything else. Check a schedule, see what I'm covering that day, and then before that class happens. So starting with a class that will happen on Tuesday, either look at the section, or in the case where, like for the next couple weeks or so, there may already be a video. So the point is, get yourself up to speed as best you can. There isn't time during the 75 minutes that we have, especially if I allow time during class, which I still think is a good idea, to talk about problems. I'm sure that's something that you guys want, to go through every detail. At a lower level class, you can do that. Not at this level. Ever since I've been at USM, there's been a tendency to be it seems as though what students do is put the professor in a position where the only opportunity for learning a material is based on what happens during those 50 or 75 minutes. And again, lower level, that's possible. I remember when I teach 102 or something like that, I'd cover everything during that time pretty easily and do so many examples that by the end even I was bored. It doesn't work at this level. And I didn't learn this stuff from the time that I spent in class. Class is where the process begins. And how it concludes is from you working with it after that. True learning is in the kind that I've not seen at any level since I've been here. Comes from a struggle. Comes from bumping your head a few times. I'm here to guide you through that process to make that reasonable, to make it constructive, bumping your head. If you don't take advantage of that, some of you have very well, many have not. Again, truly learning this doesn't happen. And this is something that's been discussed heavily among a department. Something that Dr. Schroeder is very concerned about, that we're not seeing at each level the mathematical maturity that's necessary for that class. I was telling his Cal 1 class when substituting, I had to explain to them, it was a revelation to them, that 1/4 times x is the same as x over 4. If that is a revelation to you, please keep that to yourself. But the point is, we have similar issues at a higher level. It's just not that dire, but still, relatively, it is. And that's what I see in the questions that I get. And that's why I've been stubborn about this, not conducting class the way that you guys are used to. I can't afford to be concerned about what you're used to. And when you go out into that, whatever you do past school, whether it's more school or a job, they don't care what you're used to either. it's about what's effective, and this has to be a two-way street, and it has not been, except in certain cases. And I'm sorry, but I have to dig in my heels about that. So if you come along for a ride, then the grade will take care of itself. If instead you just want to go about doing things the way you were before, that doesn't really fit, well, you get the grade that goes with that. And that's the deal. So these are things, again, you bring questions about, whether it's about material itself or problems, doesn't matter. Either one can be useful. And this is a particularly important one. If you're having trouble, I do want you to give it your best shot by yourself first. But once you get to a point where frustration starts to build, I often give students the guideline: bang your head against the wall twice. Try once, distance yourself from it, try again. Sometimes that is enough. If not, then you should start looking at other resources. I am one of those resources. Use me. But you're welcome to use other resources too. There are many. There are many of the other numerical analysis textbooks out there can be found as bootleg PDFs. I'm sure mine will be one of these days too, and that's why I'll get nothing for royalty checks. But I didn't do this for money anyway. So any kind of resources you're accustomed to seeing for other classes are out there for this material too. Maybe not in this particular book because it's not published yet, but a lot of the problems I give are pretty similar. But the point is, be timely about it. Don't wait till weeks after I've covered that section to a point where your frustration has boiled over. That's not constructive. And the thing is, so as far as what's going to happen, and this is something that I'm not yet setting in stone because this deals with your grade. Okay. Because the midterm is junked, the midterm was to be worth 30%. What I'm provisionally doing is saying, well, I don't want to make the final. I didn't want to make a final 70%. Dr. Schroeder might have wanted me to do that, but I didn't think that'd be reasonable. So keep attendance and final the same and distribute the other 30% among now there are 4 homework assignments. One discussion I had with a colleague brought about the idea of, instead of doing that, keeping the homework the same, and then the other 30% is devoted to since we're already to halfway point, halfway to that would be to the end would be 3/4. Give a take-home test. I'd have to figure out the timing of it and how it affects everything else. I thought it might be a good way to get you guys to help you guys stay on track. If you have that looming item of a take-home test rather than in-class test, which would be far more pressure still. So what I would like to know is there would there actually be a preference for putting that in, a take-home test, as opposed to now making the homework way more than it did? What? Okay.
How similar would the take-home test be to the final?
That's actually a really good question. Well, okay. Well, one thing I can tell you right now is the problems that I had previously put out there for the midterm, those kind of problems will appear on the final. Well, okay, the final Okay, I'll make a note of this because I want to put this in writing. Okay. Final. I'm going to break this down in two parts. Those of you who took 285 with me will find this familiar. So one part is like, I wouldn't really say it's like the exploration. It's more like the exercises, except not the ones that deal with MATLAB, because I'm not going to have you guys coding during the final. So that'd be one part. And the practice test that I put out there for a midterm, I just realized I took it down. I'll put it back up as a practice final that's in progress, and I'll add to it. So that'll give you you'll have an idea as to what kind of problems those would be. In other words, problems that can be worked out on paper. And then the other part is like the concept check questions. Like when I taught 285, I did on the final, it was a second section called the lightning round, where I gave a whole bunch of short answer questions about the concepts of a course. And you had to answer a certain number of those. So it would break down roughly 50% this, 50% this. And I will include that in the practice also. So you'll see what kind of questions there are in the final. Now, as far as the if I do a take home, I don't really have a definitive opinion on that, because I think what I would need to do is, unfortunately, because of time, because I have given take-home tests in this class like years ago, but they were actually kind of like the homeworks you're doing now. I didn't collect homework back then, and therefore there would be like a long period of time for them. I'd probably make this more of a short burst, like something like it would all happen within a single week. But in that case, I need to give problems appropriate to that time frame. So. Okay, well, that's what we're trying to figure out. And actually, because I would be happy to put this to a vote as to what would be preferable. But yeah, I think what I can tell you, because obviously I want this to be informed. So we're talking the halfway point between now and the end is right around here. I would need to adjust the assignments accordingly, but that's fine. I can do that if that means obviously changing a due date or changing the number of problems. What I might do is take problems that I originally would have had in mind for a homework and put them on a take home instead. The coverage would be like chapter 2 and looks like most, if not all, of chapter 6, based on the timing of it. So then the final would be, well, final is going to be comprehensive. It's going to be pretty distributed among everything. Chapters 2, 6, 8. Okay, so, but I can see what I'll probably do is, probably something where I would assign it on a or like post it online on a Tuesday and have it due like on a Thursday, something like that. So therefore, the problems would not be. It's somewhere. I guess the best thing I can tell you is somewhere between the level of a problem that I would give on an in-class test and what you currently do in the homework. Because the amount of time pressure is intermediate to that. Okay. Also, these would be the kind of problems that can be worked out on paper, because they'd be kind of like the problems that I would like to put on a midterm. since this is happening in place of a midterm. So the problems I put out previously for practice midterm, it probably would be somewhat more difficult than that, just because you're able to do them with open book, open note. But I wouldn't go far beyond that. So hopefully that's something to go on. We have like 16 of the 21 people here. Well, just initial feelers. How many would prefer having a 30% go to this kind of take-home test? Hands high so I can really tell. 1, 2, 3, 4, 5, 6. Coast?
Mine is down.
Sorry, what?
Mine is down.
Okay. Carade? Your window's really small. I can't see.
I'm sorry, my hand is down.
Oh, okay. All right. Well, that was a minority, unfortunately. So, okay. Well, okay. Well, yeah, okay, so we had 1 vote from the coast, and we had 6 or 7 up here. 1, 2, 3, 4, 5, 6. Okay. I won't make any final decision right now, but I just try to get a feel for. So if you guys have questions about this one or whatever, or concerns, please bring them to my attention, and then I will make a definitive announcement on Thursday. I mean, obviously it's kind of a big deal, so I wanted to take my time with it. But okay. But at least by Thursday, we'll know for sure what's happening with the other 30%. Okay. Now, okay. Whoops. Also, there's. Well, I'm going to put out an email to the class anyway, because there are some people who are not here, and they should have a chance to weigh in also, even though they really should be here. Okay. Now, if we take a look at the results of what I sent out yesterday, so thank you to those 7 or so of you who responded. Actually, let me make this a little bigger if I can. Okay. So as you can see in this, so what I have here is the union of all the responses. As you can see in 2.2, there was a lot. So what I'm going to do is, for today, as much as time permits, and there may not be time to discuss all of these, but I will try to some extent. Now, one thing I want to, and some of these are related to each other, so that can help. All right. Now, one thing I want to point out about floating point arithmetic section in particular is recently I've put in some new examples, in particular about toward the end of a section. Here's a new example about loss of precision and how that affects arithmetic operations, which relates to this exploration and the next one. These two are actually quite closely related to each other, because they both deal with addition, and of the problems that can arise from that. Also, for underflow, overflow, this example gives you an idea of how, even though you're dealing with numbers initially that are representable, what kind of operations could lead to either underflow or overflow. Okay, so I'll have more to say about these problems, but it'd be a good idea to re-download the textbook. It's actually, I wouldn't say it's changing daily, but it's changing pretty often. And And the thing is, your questions help with that. So if I see from your question you're having difficulty with a certain portion of material, then I think, well, maybe I should put more illustration in there. And I go ahead and do that. If there's anything like that, and you feel you could use some more elaboration, something to illustrate, I'll do it. So it's hearing from you helps everybody, but especially yourself. Okay. So what I'm going to do with these problems is, well, it depends on problem. Like in certain cases, what I will do is like a roadmap of sorts. So you have some breadcrumbs to follow to get you, so that you don't wander too far away from the answer. What I'm willing to do in certain cases is actually pick some of these problems and step through them during class. And so that applies to this section, also to upcoming sections. So that's something we can do. Okay. Now, so as far as the problems that pose the most difficulty with in section 2.1, this is the first one that was mentioned, number 8. Okay, now, so I have to emphasize that I have to make sure to stop short of giving an answer away, but I'm going to try to get as close to that line as I think I can. Okay, so what I'm going to do is I'm going to be making some notes about these problems in here. Whoops. Okay, this editor is being very uncooperative. Okay. I still haven't paid for this program yet. I'm still debating. Okay, and definitely want to make this a little bigger. Okay. All right. Now, so given the conditions for a problem to be well posed, which is more desirable? Forward error to be larger, smaller, or of similar magnitude to the backward error. And I'm going to go back to those conditions for a problem to be well posed. Okay, so here are the conditions, problem being well posed. It has to have a unique solution, but this is the condition of interest, that they examine the third condition for a well-posed problem. Small change in the input does not lead to a large change in the output. Now, by change, what I really mean is, how you should interpret that is error. So we're not talking about, oh, we've solved this one problem, now let's solve a slightly different problem. The fact is, you can have the input data to your problem, like I said before, is often based on measurement. Measurement has error to it. And you don't want a situation where some measurements are fed in as input and you get some sort of solution as output, and then very slightly different input is fed in and the answer changes drastically. There's an example in this section involving linear systems, which would be a big topic for next semester, where a small change in a problem does lead to a very large change in a solution. Unfortunately, it can happen. So what I'm going to explain is what this problem is really about. So between forward error and backward error, which one corresponds to the input, which to the output? It's really about making sure you understand what forward and backward error represent. So as long as you have that straight, that then the answer to the question emerges from that. Okay, so I'm hoping that when I point out to you, well, here's why I put this problem in there. What particular part of the material am I testing you on by putting this problem in here? That gives you something to go on. Okay. Now I want to emphasize that for the explorations in particular, in most cases, the path to an answer is not meant to be a very long path. I'm not saying easy. I'm definitely not saying easy. I want to make that very clear right now. But we're not talking about a very elaborate process from start to finish. Now, in other words, only a very small number of steps are involved. Now, thinking of a right step to take, that can be a challenge. But it's often seizing on one key idea that puts you on the right path to a solution. Now, an exception to that would be certain problems involving coding. Like, for instance, the day of a week problem from homework 1. That was definitely something elaborate. But generally, these are more along the lines of like performing a single task. The exercises at the end of a chapter are meant to be more elaborate. Okay. Does anyone have any questions about, and certainly you can jump into questions at any time. Anyone? All right. One thing I want to make clear about homework submissions. Whoops, I do not want his question marks. Why do you think I want question marks? Who does that? Okay, if, since many people have turned in something for homework too, you can, but please, preferably, if convenient, send the whole thing. Because I've had a situation where you've submitted something on a certain problem and you realize, oh, you did it wrong, and you go back, and then it becomes more difficult to piece it together because you're submitting these by email, and I have my folder where I put all the submissions. If I could just, it's easiest if you just send me something and you can say, okay, now I can ignore what you sent me before. So if that's not possible for some reason, please let me know. The point is, I want to make sure I'm grading the right thing. Okay. All right. 219. Okay. Now, for this one, the problem asks for estimate of the relative forward error. Okay. So the idea here is estimate of relative forward error is given by, and I say approximately equal because again, all of this is just estimates. Relative backward error times what? Which condition number? Relative condition number. Okay. So that's one key idea. For a condition number, use equation 2.1. That gives you a way to estimate the relative condition number for a particular function. So the idea is you're given a backward error in a problem, or a bound on a 0.01. You can get an estimate of relative condition number, so simply the product of those two is going to give you your estimate of a relative forward error. Now, for the last part of a question, checking if this estimate is valid. So So what you can do is use extreme cases, meaning that so, whoops. Okay, that's really weird. Okay, oh, I see now. 10x naught minus x naught is equal to plus or minus 10 to the minus 2, which is the size of a relative backward error, times x naught. So what you can do is, so in other words, you're looking at x falling in within a certain interval that's centered at x naught, which happens to be equal to 2. So what you can do is use this to find x values of x naught hat that are at the opposite endpoints of this interval where x lies. And then what you can do is substitute into your functions f of x and g of x to get actual forward error. And the question is the estimate at least in the ballpark? So I'm just looking for your observation there. So here we have just an error estimate based on an estimated condition number. And then since a function is so easy to evaluate in these cases, we can see what the actual, because the actual error would be values that like f of x naught hat minus f of x naught divided by f of x naught. Okay. So I say actual forward error, and I want to make clear this is relative forward error based on the definition. Okay. All right. So that's the map through that problem. Okay. Okay. Yes.
That one, if you just use the calculator to sub in and stuff, were we supposed to like show that?
No. I mean, just like a final result. Okay. Like your estimate is this, your actual relative error was this. Are they close? That's all. Yeah, like the individual steps, I trust that you, yeah, well, I'll know from your answer if you did it properly or not. So. Yeah, because I figured like if you're doing this in MATLAB, it's a diary. Right. And yes, but I'm fine if if there's anything that you could do in a calculator, I'm fine with not having a diary. So yeah, I'm not gonna have you like take a picture of your calculator screen. Okay, any other questions about this one? Okay, number 11. Okay, now based on what I've previously said, unfortunately there is not much more that I can say. But I'll just point you in that direction. God. I really need to email whoever wrote this and give them what for. I mean, for most parts, works very well, but sometimes, like, okay. So use the rule for derivative of inverse function. And that's 1 over f prime of f inverse. Okay. So in conjunction with equation 2.1 for estimate of the relative condition number. So that's really what I'm looking for. And when I had gotten questions on this in the past, what I noticed is that unfortunately there would be some carelessness with the algebra. So watch your algebra on this one. But really, these are the pieces for putting that one together. Okay, and keep track. What's the input? What's the output? And because so this problem, because it's working with the inverse function, is meant to kind of scramble your brain a little bit and force you to really think through about because in generic terms we're saying here's your input x, here's your output y, which is f of x. But now what are we trying to compute? F inverse of something. So that flipping around is meant to make you think a little harder about what represents the input or the output, and making sure you keep that straight, regardless of the situation. Right, so this determines what plays a role of x, f of x in this problem. So it's kind of stood on its head. Okay, number 14. Okay, what I'm going to do with this one is I'm going to carry out a part of it. So what we're doing here is trying finite difference formulas for derivatives for various values of h that I specified. So in this problem, f of x is equal to sine x. Okay, x naught equals 1. So the exact answer is f prime x naught is equal to cosine of 1. So go ahead and compute that so you see at least this is what you're supposed to get. So then your so your approximations so there are two formulas here. Let's work with one of them. Okay. Okay. So the idea is you go ahead and try these out, and it'll be easier to do it on MATLAB for the h's that you're given for this formula and the other one that's given in the problem, the center difference, and what is supposed to happen as h goes to 0? As h goes to 0, and this is meant to test your understanding of convergence. What does it mean if the error is h, or big O of h squared, as h goes to 0? So what is so you can see when you compute these, you can also just subtract them and get the error. What is supposed to happen to the error as h goes to 0? Like because for instance, if the error is order h, so as h increases by a factor of 10, so does the error roughly. If h, in this case, h squared decreases by a factor of 10, then the error should decrease by a factor of roughly 100. Does that happen? And if it does not, why do you think that is? Okay, so that's really what's supposed to happen with that problem. Okay. Anything 2.1? Let's look at 2.2. We may not have time for all of these, but I'll do what I can. Okay. Now, in 224, I got a number of questions about this one. Okay. So you're given a specific decimal floating point system, and the question is, what are the largest and smallest positive numbers? So the form of your floating point number is mantissa times 10, which is your base, raised to some exponent e. Where e has to be within a given range. Now, I don't think anybody had trouble with the second part of the number, as far as making this largest or smallest. Where people seem to have difficulty, what are the largest and smallest mantissas? Do not assume normalization. So in other words, the smallest mantissa is not 1. So the thing to keep in mind here is it's a string of digits. In this particular problem, the beta is equal to 10, so it's a string of decimal digits. But also it is a fixed number of decimal digits. How can it be made largest or smallest? Digits run from 0 to 9, and any of these digits are allowed. Because we're not normalizing, think of it having, like, since p equals 5 in this problem, you have 5 spots. You're putting a digit in each spot. Those digits are allowed to be any number from 0 to 9. But the only constraint here is it has to be at least positive, so you can't fill your mantissa with all zeros. Other than what I've just said, there's no other limitation. But again, I'll reiterate, mantissa is not 1. So as an example, but also want to keep in mind, you only allowed 1 digit to the left of decimal point. So the mantissa, dang it, okay, this thing is being aggravating again. So m has this form, because it's decimal, it's x dot xxxx. Because there are 5 digits, you have 1 digit to the left of a decimal point, 4 digits to the right. So you're filling in here whatever's going to make this either as large as you can get or as small as you can get. So as an example, I could do, for instance, 0.1000. So you're allowed to do this because you're not normalizing. That is not the smallest, but it'll put you on the path there. Okay, so it's not just the exponent part that determines largest or smallest number. It's the mantissa you have to think of also. Okay. And this goes in hand with 2.2.7. The number is normalized in that case, and what that means for the mantissa then. Okay. Also, there are formulas below for underflow and overflow. That's what we're looking for. Is overflow and underflow are the largest and smallest possible numbers you can have in that system that you can represent exactly. So whatever you come up with ought to be consistent with those formulas for the floating point system that you have in this problem. Okay. Okay, 2.2.6. Now, this is strange. I thought that. Hold on. I thought that I had put something in here about this problem. And now I'm not sure why it's not there. Oh, okay. Okay, I'm going to close down this PDF and reopen it. Because I put an example here for this problem. And I'm not sure why it's not there. Okay, maybe I'm opening a wrong one. Okay, sorry, just need to make sure. Okay, that was updated today. Oh, okay, it isn't here. So I'll be getting real quick about this problem, number 6. New example added right above. Okay, so let's take a look at that. I'm hoping I will put you on the right path there. Okay. 8 and 9. Okay, here's 8. Okay, value of underflow for a floating point system, both with and without normalization. So this. Okay. Now, for this, refer to the definition of underflow, and actually, this is just underflow. So there's a formula for it involving that'll take care of the exponent part. It involves the smallest possible mantissa, and that is equal to 1 if normalized. Formula is given on that page. Let me make sure. Okay. Okay. Say on this page where the problem is. For mantissa if not normalized. And this is related to 2.2.4. What was the smallest mantissa in that case? It's so the same point about what makes the smallest possible number, smallest possible mantissa, that's coming up again and again. In the hope that after working through all of these, that it starts to sink in. So making a smallest number deals with the mantissa, making that small as you can, and also the exponent part, making that as small as you can with the smallest allowed exponent, like minus 1022 in this case. So the case of without normalization gives you the actual smallest number that MATLAB acknowledges. Okay. And this actually comes up again. Stop that. In the next problem, looks like I'm talking about most of these towards the end. Okay. So it's a similar theme. So if numbers from a table cannot be represented, like instead you get inf if it's too large, or you get 0 if too small. Try over powers of your base, which is 2 in this case. So, like if you try 1 power less or 1 power greater, or something like that, to get an idea. This is deliberately meant to get you to experiment with floating point numbers. Now, because that's how real mastery comes from trying things. It's not about doing following some direction from me. It's actually what you do that is not directed by me that really determines how well you learn these things. Okay, but that means I'm giving you room to experiment. So it's not something that I'm going to be judging very harshly from a grading standpoint, unless what I see is a lack of effort. Okay, that's a different story. As far as explaining any discrepancies, all I'm asking for is an effort. Just try your best shot. If you can't really figure it out, that's okay. But one thing I can call your attention to is how are numbers like infinity or not a number so this is related to discrepancies with the table. Okay. Okay. That was something I talked about at one point in class, but also it's something that you can also look up and find out how that's done and how that affects what numbers can be represented. Whoops. Let's zoom in a lot. Not that much. Okay. Okay. All right. So for 11, 12, 13, new examples are added that hopefully will help with these. So I know these in particular gave some fits. So the thing is, for number 11, the kind of numbers that RAND would generate would not cause any issue with lack of associativity. But for 2.2.11, dang it. I don't know why. I did not ask for a subscript. Stop that. Only numbers of widely differing magnitudes create an issue. Numbers of a similar magnitude are not. You're not going to notice any issue with the loss of precision there. Okay. So problems happen when digits are lost due to rounding. Again, examples that I have that I added will illustrate this effect for small cases like just adding 2 numbers. Now what if you're adding more than 2, like 3 for associativity, or a list of numbers like in 2.2.11, and also 10. This relates to that too. And then for 2.2.12 and 13, as an example, I gave a hint before factoring. I'm going to put this, I said this in words before, but now I'm going to write it out. Okay. So if you're computing z, which is the square root of x squared plus y squared. And what I could do is, if I want to factor something out, anything out at all, I even said in class my exact words, you can factor out a w. Yes, there's no w, but you can just put one in there, as long as you compensate for it. Because as you can see, the two expressions are identical. All I've done is multiplied, and divided by w. But what that lets you do, I want to be outside the square root. Okay. Now I can factor out, because the thing is, a sum of squares you can't really do anything with algebraically. But if there's something you factor out, then you can separate these square roots. And sometimes students try to separate a square root of a sum, and you can't do that. But a square root of a product, you can. So so the question for you to answer is, what should W be? To put in a situation where you're not having an operation that causes overflow. And to test your idea, assume not only x is greater than y, but extreme case helps. Assume x is very large. Very large. Also assume y is very small. Some ideas that students have put forth end up falling apart under the assumption that y is very small. So if your idea handles this case well, it should handle every case. This is for 2.2.12. The same idea, just generalized to having more than two numbers, will get you through 2.2.13. Okay. For number 15, for the algebraic trick, which you've all seen at one time or another, exploit this generic relationship. A plus b, a minus b is equal to a squared minus b squared. Because what you're dealing with is an expression with a quadratic formula involving a square root. So if you can, so if you imagine one of these being at square root, you can multiply and divide by something to bring about something that causes it to be squared, and that aids in simplification. If I go further than this, I'll give it away, but I'm hoping that puts you on the right path. Okay. For 2.2.16, here's what I'm going to do. Two formulas for variance. I'm going to show you how you can do one of them. Okay. I'll also put something in this diary. Now, if I do this, 1,000 numbers using rand n, that's going to give me random numbers distributed between mean 0 and standard deviation 1, but I don't want that. I can scale by the standard deviation, and then I can add the mean. Whoops. Okay. So that's how the random numbers are generated. So first formula, so that'd be 1 over n sum of xi minus the mean squared. Okay, so it's this formula right here. So the easiest way to do that, now n is equal to 1,000. I'll just put it in a variable for compactness. Probably the easiest way to do this is, I'll call this S1 for the first standard deviation. That would be 1 over n times the sum of x, your vector x, And you need the actual mean. Well, the MATLAB function mean will give you the mean. But I want to square all the elements of that vector. So I can do dot squared. So now I've x subtracted from mean. All elements are squared, and that's the dot square does that. You need the dot because this is a vector. And then the sum function will sum them up. And notice what you get is near 0.01. Actually, I should have called this V1 because it's a variance, not a standard deviation. Standard deviation is 0.1. Therefore, variance is supposed to be of a sample is supposed to be 0.01, and sure enough, it is. So the other one should be also. Okay. So for this, whoops. See diary, the October 12th diary for that. And 2.2.17 goes hand in hand with, I talked about this earlier. So in light of what we observed in that problem, and for that, you must keep in mind that h is really small. And what can go wrong with floating point arithmetic? Various issues have been highlighted in this section. Which one applies? Given that h is very small. Okay. Sorry I'm going this fast, but I'm hoping that it gives you some information. And unfortunately, time is running short. I want to say what I can about problems of the exercises here. So exercise 3 in MATLAB, use for loops. So for instance, I'm going to pick a value of n. Let's say n equals 1,000. I didn't really specify in the problem, but that will work. And I will start you off with like a allocation of a vector. So x would be like a zero vector of length n. So now what you can do is use loop to fill in. And so for instance, you could create two vectors like x1 and x2. I'm going to call this x1. And another vector x2 because you are creating this in two different ways. And use loops to fill in. Dang it. Stop it. Dang thing. To fill in x1 of I or x2. So you're filling in each element of these vectors, but you're doing it in a different way, using either addition in the first part or multiplication in the second part. So what happens when you do that? Now, since you're using a nice number for spacing 1,000 points, you know what the spacing is supposed to be. These are elements in 0, 1. Spacing is 1/1000th. So you know what you should get. Do you get that? And if one of these does not produce that, why do you think that is? Okay. One key here is from a later exercise. Zoom in. Okay. Dang it. From exercise 4, 0.1 cannot be represented exactly. And similar for other powers, negative powers of 10. Integers can, but positive powers, but not negative powers. While on the subject of exercise 4, check example in the rounding chopping section about 2/3. Floating point representations of 2/3. See how what happens with 2/3 in decimal. In decimal happens to 0.1 in binary. Similar patterns in the digits. You can see this from the hex format. In fact, I would venture to say, I gave that as a hint to the problem, that once you take a look at the 2/3 case, see what happens there of chopping or rounding, what's different, and then look at the hex format for 0.1, you'll be able to tell how it would be different with chopping without even understanding what the hex format means. Look at the pattern in the digits, and that will tell you what you need to know. And it corresponds very closely to 2/3. That's why I pointed you to that. So understanding what you know perfectly well for decimal and extrapolating from that to binary. And I know that I've gone over time. So here's what I'm going to do. I'm going to add something to this document for exercises 5 and 6 before I put it on the site, on the lectures page. Now, on the schedule, we only have one more class before fall break. The class after fall break, we are putting this to bed, right? Okay. And then, be sure to keep the questions coming. And as a reminder, for Tuesday, Lagrange interpolation is the subject. So before class, either watch the video from it, from when I covered before, or look at the section. Bring your questions. Those of you who started homework 3, look at those explorations. Bring your questions about those. So we're going to get this section nailed down for everybody. Okay.